critical numbers. Of course, if they exist. Obviously, I have to determine the first derivative in both, no matter what source. So the first derivative will tell us what is happening here. So f prime of x will be 6x squared plus 2x plus 2. Obviously, this is always defined. It's a polynomial function, it's always defined. So from source number 2, we will not find anything. So our only chance, or the function may have a critical number if this equation has solutions. If it doesn't have solutions, then so 6x squared plus 2x plus 2 equals 0. Of course, I'm going to divide by 2. And I have 3x squared plus x plus 1. And when I use the quadratic formula, negative b, which is 1, plus or minus the square root of 1 minus 4ac, I'll say not real. Because the equation has no solutions, it's never 0, the left-hand side will never equal 0, I get an imaginary number, 1 minus 12. This function has no critical numbers, done. So, no critical numbers. I can say, I don't have to write it at this point because we haven't explored that avenue. No max min. So you know, you don't even have to graph it. You know way ahead that you will not have a max min. Let's look at a rational function this time. So let's say f of x equals x minus 1 over x squared plus 4. So again, this function may have critical numbers coming from two possible sources. No matter what, I have to find f prime. So f prime of x. Top prime is 1 times the denominator minus top times the denominator prime over the denominator squared. So x squared plus 4 minus 2x squared plus 2x, everything over x squared plus 4 squared. Negative 2x squared plus 1, negative x squared plus 2x and plus 4 over x squared plus 4 squared. You know me. Knowing me even a little bit, you know what I'm going to do. I refuse to work with a negative leading coefficient. So now, two possible sources. Not so fast. This is never undefined. How do I know? This is always positive. It cannot be 0. So this rational function is always defined. The denominator will never be 0. So no critical numbers coming from that source. But what about f prime of x being 0? I know that a fraction is 0 when the top is 0. So x squared minus 2x minus 4 equals 0. I use the quadratic formula. So 2 plus or minus 4 minus 4ac, 16 divided by 2 times a. So that's 20. Obviously, I found two solutions. I have to simplify. 2 plus or minus, since it's 20, to the square root of 5 divided by 2. You cannot try to simplify this. Please don't do that. You either separate the fractions or you factor. So the simplified form will be 1 plus or minus the square root of 5. These are the critical numbers of the function. And they come from f prime being 0. Okay, let's also look at a natural log or an exponential. I think we got the idea.
Can you slow down just the tiniest
Yes,
bit?
yes.
I have a question.
Yes, please. I beg for questions.
Okay, did you not include the denominator because it's always going to be greater than 0? Is that why?
Okay.
I just don't get how you got the x squared minus 2x minus 4.
Perfect. A fraction is 0 only if a is 0.
Okay. All right.
Any questions? I think there was one more question, but I think I was talking at the same time and I didn't hear. Please ask any question, anything. Are we okay?
Yes.
So please remember, this will save you a lot of time. A fraction is 0 only when the numerator is 0. If the denominator is 0, we are in big trouble. You can say we're not, the function is. I agree. Trying to be funny, sorry. I know, I'm not that funny. I'm learning. I'm trying. Okay. Let's look at some other function with the same question and then move on to the next type of problem. So here's the same question. Find critical numbers if the function has any. Okay. Obviously, in this particular case, I have to do, as you said, slow down because this is a totally different type. On the first one of my devices is just acting up a little bit, the one that records. Sorry.
So here I didn't mention anything because this function is a polynomial function and it's defined everywhere. Here I said it, but not from the very beginning. This function is always defined. X squared plus 4 is never 0. This is a positive number. When you add 4 to a positive number, it will never be 0. But here I have to say, wait a minute. This function is basically natural log x divided by x squared. One problem is already there. And the other problem is that x has to be greater than 0. This one solved this problem as well. So the domain of this function is 0 to infinity. Okay. So remember, when we graph or think about functions or do anything with functions, the domain is crucial. It has to be in the back of our minds at all times. Okay. Knowing that, now I'm going to differentiate. But I want to differentiate this. It doesn't really matter. But I will differentiate that. So f prime of x, I bring down -2. I subtract 1 from the power, and I multiply by natural log, and then plus x to -2, and I differentiate the second function, which is 1 over x. It looks nice, but remember, if you don't fully simplify it, you're going to have difficulties in solving the equation f prime equals 0. So this one is basically -2 natural log x over x cubed. And this one is also 1 over x cubed. I like it. I copy the denominator. So this goes to the top. So I will have 1 minus this. Which, of course, you know me, I don't like negative leading coefficients. This is not a real leading coefficient, but that's okay. It can stay for now. Okay, so this is final. Now we know that critical numbers come from two sources when this is undefined. But this is undefined, so f prime undefined at x equals 0. But who cares? The function is not defined at 0, so no critical numbers coming from that source. The function must be defined at 0, but it's not, so no critical number. The other option is when f prime of x is 0. Again, a fraction is 0 when the top is 0 only. So 1 minus 2 natural log x equals 0. So now I have to work on this equation. I move 1 to the other side, or 2 natural log. It doesn't matter. -2 natural log x equals -1. Of course, I will multiply by -1, or better, I will divide by -2. That's even better. So I have natural log x equals 1/2. But now I have to remember how to convert this into an exponential equation. Any log equation can be converted into an exponential. Any exponential can be converted into a log. How? The base, which is e raised to 1/2 equals x. E, we don't write it, we know it's there. E to 1/2 equals x. So that's our critical number. So this function has one critical number, which is the square root of e. X equals the square root of e, critical number. Does this give a max min? I don't know yet. And I'll show you how we know if it does. That's how we determine max min. That's not what I said. That's how we determine critical numbers on the path to determine max min. Okay. Next concept here that we have to look at, and let's look at a function. I'm going to graph a function, and then we'll look in the book for different examples. This is a simple function because I like to talk about max min. So this is max min, and each is of two types. Either local, also called relative, both of them. It can be a local max or a relative max. They mean the same thing. We use them interchangeably. Or absolute, also called global. So there is a minimum that is local minimum, or relative minimum, same thing. And there's also something called absolute minimum or global minimum. Okay. These, the absolute, the local and the relative, cannot be at the end of the interval. The local ones never at the end of an interval. Never. These can be anywhere. Middle, end of the interval, anywhere. But the local and relative can only be where the function exists on both sides. So here's an example. So here's a function. And you see that the function is increasing between negative infinity and -2. It's increasing. Between negative infinity and -2 for x, the function is increasing. Then it's decreasing between -2 and 1. And then it's increasing then it's increasing between x equals 1 and x equals 4. That is the trend. We also notice two things here. That right here, the function has a horizontal tangent, as well as here. Horizontal tangent, the slope of the tangent here is 0. So f prime of x is 0 at this point, at -2. Maybe I should write it like that so it's clear. And also here, f prime of 1 is 0. The horizontal, because of the horizontal tangent. Okay. I'm going to give some names because it will be easier for me to refer to them. So I'm going to call this point A. I'm going to call this point B. Let's say this is C and this is D. Point A is a local max. How come? I can show the open interval. The function exists on both sides, and the function values left and right are smaller than this one. This is a local max. Also B is a point of local min. If you prefer relative, you can say relative max, relative min. Why? Because again, I can show the open interval and the function values are at least equal to or greater than that value at 1. So how will I give the point of local max? I will say -2, comma f of -2. That's the point of local max. -2 is the position where the maximum is. F of -2 is how much the maximum is. The same thing, 1 comma f of 1. 1 is the location of the minimum, and how much is the minimum, it will be f of 1. What about point C? Point C is -4 comma f of -4, and this is an absolute minimum for this particular function. This is our function f of x, of course. So there is no other value lower than it. So this is the absolute. It's not local or relative, because I cannot show the function on both sides. I can show the function exists on this side, but not on this side. And as I mentioned, the local or relative can never be at the end of the interval, but the absolute can. The same thing with D. Point D is absolute max, and the absolute max is 4 comma f of 4. This is the location, and this is how much. Any questions?
What do you have pointing to f of 4?
How much?
Oh, okay. Thank you.
The y value. So this is the location and this is the y value. How much is the actual max or min? Anything else? Other questions before we look at a graph? Before I continue, I just want to give you the heads up. So let's look at point A for a moment. Here's point A. Notice what happens. The function is increasing on this side, and then it's decreasing on this side, and that's why this is a local max. If the function is increasing, can you say anything about the derivative, the first derivative? Remember, the first derivative is the slope of this tangent. Is it positive or negative? Is it positive? Positive. And then all of a sudden is how much?
0.
Perfect. And what happens after that?
Goes negative.
Right. So this is a typical situation for a local max. The derivative can be 0 and f prime changes sign. For the local max, as we discussed, from positive to negative. Or the second possibility is the derivative is undefined. And f prime changes sign. From positive to negative. Those will be guaranteed to be local max, those points. So at a local max, two things may happen, one or the other, not both. So the derivative is 0, in other words, there is a horizontal tangent, and the derivative changes sign. If it does not change sign from positive to negative, but it's both on both sides positive or on both sides negative, that will not be a local max. And I'll give you an example in a minute. What is the second possibility? When the derivative is undefined at that point, where the function is defined, of course, and the derivative changes sign only from positive to negative, that is guaranteed to be a local max. So here's an example. I wanted to talk about x cubed. So when we differentiate x cubed, that's not a problem, you'll say, that's fine. So, oops, so it's 3x squared. But when you set this equal to 0, you get x equals 0. But 3x squared is always positive. So, because it's always positive, from here, x equals 0, not a critical number. That creates a maximum. A max or min. It is a critical number, yes, but it's not a critical number that will produce a max or a min. Here's the graph. Here's the graph of x cubed. See what this function does? Never, its derivative never changes sign. Although there is a critical number at 0. Its derivative is 3x squared. This will always be positive. As you see, the function is always increasing. It has a critical number, but that critical number does not change into